Okay, in order to further learn more about gravitational potential energy, we have to discuss the concept of work. And we have to review that concept to those who already know it. And learning about work really stems from this question: how to increase the kinetic energy of an object? And the answer to that question is to make it accelerate in the same direction as its displacement. If that object is moving to the right, its acceleration must be to the right, so that the whatever initial velocity it has will grow in that same direction. So to elaborate further, if the object is, so wait, I want to make that line straight. If the object is displaced to the right and it has an initial velocity to the right, if your acceleration is also to the right, then you expect that that initial velocity will grow, and that also implies that the kinetic energy of that object will also grow, because our initial kinetic energy is related to velocity through this formula, as well as our final kinetic energy. And so our change in kinetic energy will be greater than zero, or will increase, if our final velocity is greater than our initial velocity. And we can achieve that through accelerating in the same direction as the displacement. So how do we accelerate an object in the direction of its displacement? Well, we act a non-zero net external force on that object. And not only that, the direction of that non-zero net external force must be along the direction of the displacement. We know that to be true because of Newton's second law, which is actually a combination of two other expressions for the x component and the y component. Take the example of this problem. This box is displaced to the right, so it has a displacement to the right direction. And as you can see, there are three forces acting on this object: a pushing force to the right, a normal force upward, and a gravitational force downward. At first glance, you will clearly see that the normal force cancels out the gravitational force, because the displacement of this box is to the right, not up or down. And as you can see, the pushing force is also to the right, so the direction of the pushing force and the displacement is the same. So expect that there will be an acceleration for this problem, which is also directed to the right. This is the system schema of the object, and if we focus on the box, there are three external forces. And by using the Newton's laws, we will see that the pushing force is equal to the mass of the box times the acceleration along the x component. For forces along y, there is no acceleration along the vertical component, so it doesn't really matter what this says here. The only acceleration is along the x, so we write Fp over m. Okay. Let's look at another example. This time, the pushing force is not purely horizontal, but set at an angle below the horizontal. So what happens is, if you remember your trigonometry, this pushing force has an x component in the same direction as the displacement of the box. We can solve that to be Fp cosine of phi. It also has a y component directed downward. So We still have one force along the x, but we now have three forces along the y. But these three forces don't contribute to anything because the acceleration is still zero. And by anything, I mean we're just trying to calculate the acceleration. Solving for the acceleration, we now notice that the acceleration is Fp cosine phi over m. Remember that when the force was purely horizontal, the acceleration was Fp over m. So clearly, the acceleration when the force was purely horizontal is greater than now that it is set at an angle below the horizontal. Because cosine phi is always either 1 or less than 1, and in this case, it's definitely less than 1. Therefore, this acceleration is much less. So what is our takeaway? Well, before that, this is another example. In this case, the box is falling down, free falling. There's only one force acting on it. And it's not a horizontal force, but a vertical force. And the acceleration is Fg over m. In this case, the displacement is downwards, and the external force, the gravitational force, is also downwards. So expect that this object will accelerate downwards, and the kinetic energy of the object will also increase. Before that, let's look at this. What are your takeaways from the previous example? We learn now that the force that is parallel to the displacement of an object causes a greater acceleration than the same force acting at an angle to the displacement. So if you want to achieve maximum acceleration, you have to push with a force that is parallel to the displacement. And we also learned in this blue text that forces perpendicular to the displacement do not contribute to the acceleration along the displacement. Not at all, no contribution, like the normal force and the weight in that box example. So let's go back here now. Clearly in this problem, in this graph, we see that velocity is increasing. There is a positive slope, and therefore it is accelerating. And we all know that the area under the curve it represents displacement. So clearly, an object with a non-zero velocity, whether constant or changing, must have a displacement. In other words, it doesn't make sense to say that when you see an object and you say that object is accelerating, but then at the same time you say that the object is not being displaced. Look at an object around you. Look at stationary objects around you. Those objects that are stationary, they are not being displaced. Would you say that they are accelerating? From your frame of reference, no, they are not accelerating. So, in order to really say that an object is accelerating, then that's tied up with the object being displaced. So when you say that the object is accelerating, then surely that object must be displaced. Maski gani constant ang velocity displaced yapon. The only time that the displacement is zero is when the object is also not moving with a velocity of zero. So A and D are closely tied, and force and acceleration are closely tied as well through Newton's second law. Therefore, if A and D are closely tied and F and A are closely tied, then surely F and D are closely tied. So force and displacement are closely interrelated. So we're going to focus on those two concepts, force and displacement. So here, as I mentioned in one of our takeaways, This force is situated at an angle from the displacement and not necessarily purely in the same direction as the displacement. This force has a parallel component. We call that F parallel. Parallel in the sense that it is in the same, this component is in the same direction as the displacement. And trigonometry tells us that that is equivalent to F cosine phi. This force also has a perpendicular displacement, a perpendicular direction, perpendicular component, there, F sine phi. So what did I write here? For an object that accelerates along its displacement, only the force component that's parallel to that displacement is causing the acceleration. So if you want an object to accelerate in the same direction as its displacement, there must be a force, at least a component of that force that is parallel to the displacement or is in the same direction as that displacement. Here, the perpendicular component doesn't contribute to the acceleration along the displacement. F sine phi has no contribution whatsoever to the acceleration along the direction of the displacement. So therefore, what are your takeaways? Only the parallel force or the force that is parallel to the displacement is causing the kinetic energy of the object to increase. Forces perpendicular to the displacement do not cause a change in kinetic energy of the object that's moving along its displacement. It's kind of redundant, but I just want to overemphasize that fact. Let's look at this example. Is there an increase in kinetic energy in this object? Well, so this does tell us that the force parallel is to the right and it's non-zero and the object is being displaced as well because it has a run. Its rise is zero, so it means that the parallel force is constant. But constant force causes constant acceleration, which is still acceleration. And acceleration causes a change in velocity. So if the object's velocity changes, then there is a change in kinetic energy. And depending on the direction of the initial velocity, and if you assume that the initial velocity is to the right, then we can say that the kinetic energy increases. But surely we can say that there is a change in kinetic energy. Here in this problem, there is still force, and there is still displacement because there is a rise and there is a run. So we can say that there is a change in kinetic energy. And in fact, in this case, the force is constantly changing, which makes the acceleration constantly change, which makes the change in velocity constantly change. It's a ruckus, but how about in this graph? In this case, there is no force, it seems. The red graph lies on the x-axis, so the force is zero. So that means that even if the object is being displaced, there is no net force acting on the object, which means there is no acceleration because force is mass times acceleration. But no acceleration means the object is moving at constant velocity. And if the velocity is constant, then there is no change in kinetic energy. So the change in kinetic energy is zero. In this case, there is a force applied and it's positive, but there is no displacement. So even if there is a force applied to an object, if that object is not displaced, then it will not accelerate. It will not increase its velocity. It will have no velocity at all. Therefore, the kinetic energy is zero. There is no change in kinetic energy. Notice that it seems here in these graphs that what's important is the area. If we want to have a change in kinetic energy, there needs to be an area below the F parallel D graph. Here, the third and the fourth graphs, there can be no area, so there can be no change in kinetic energy. And if we focus on the first graph, because it's the easiest area to figure out, area is just the product of the length and the width, or the parallel force and the displacement. This product between the magnitudes of the force parallel to the displacement and the displacement is known as work. It's given a name because it this combination of the two concepts can cause an increase in kinetic energy. So work, W, its symbol, its SI unit is joules, and its formula is F parallel times D. And what it does, it's the net work done by forces on an object causes that object to change its kinetic energy. Now we are now generalizing here because in our examples we only have one force essentially acting on the object causing the acceleration, but what if you have an object with many forces acting on it? Then we have to generalize and say that the total work done is just the sum of all the works done by the individual forces, causing overall change in kinetic energy of that object. But of course, the parallel component to the force is just F cosine phi, where phi is the short angle between the direction of the force and the direction of the displacement. So many books you see that work is expressed in this form, Fd cos phi. Can we use dot product to define work? Sure. So what is the dot product? The dot product is also known as the scalar product, and it's represented in this manner. So we put a central dot in the middle of the two vectors to denote that we are calculating the dot product. It's the cousin of the cross product, but unlike the cross product, the dot product is a scalar value. So we're not getting a vector out of the dot product. We're getting a scalar, which in my opinion makes the dot product easier than the cross product. Easier to solve. First way of calculating the dot product is now, can you now see how it looks so much like the formula for work? Imagine if A is F and B is D, displacement, and F dot D is F, magnitude of D, and cosine theta, which is the short angle between the force and the displacement. So that's why we can express the formula for work as the dot product between the force and the displacement vectors. There's another way of calculating the dot product, and that's if you know the x components and the y components of the two vectors involved. And as you can see, it's very easy. You just multiply the x components, ax, bx, plus the y components, ay times by. And you're not using matrices here because you only use matrices if you want to get a vector out of the solution. But again, dot product is a scalar. So therefore, our definition of work can be expressed as the dot product between the force vector and the displacement vector. So this is the last slide. What if F is not constant, but it's a function of the displacement? Here we're using R for our displacement, and because recognize that this needs calculus to solve, and we cannot use D because D has a special meaning in calculus. In fact, it's used for derivatives, right? So here is the formula for calculating. We still need to calculate the area under this graph. Mentioned in the previous slides that it's the area that matters. And here, even if the force is not constant, it's still the area that matters. But in order to solve for the area, you create infinitesimally thin rectangles and you add up all those rectangles. And the way to add is to use this symbol, which is the integral of f dot dr. But we will use that formula when we calculate the gravitational potential energy. But for now, we'll end the video here. Thank you.